Okay, welcome back. I am curious if you were able to get through the emotional grief of not having structural analysis on Friday.
It was tough.
It was tough.
I didn't know where to crack my jokes before class, so I just came here by myself.
All right, so I did post that video going through virtual work. We're going to give a quick recap of that today, and then we're going to start getting into the examples. A little bit on housekeeping. So all the attendance grades are up to date. I counted everybody present for that lecture because, I mean, you all didn't get to choose for that being online, so I just assumed everybody was there. All the outstanding homework has been graded. For project submittal number 1, my goal was to have that graded either by Friday or Monday. Definitely by Monday because I'm assigning submittal 2 on Monday. It's not going to be due until the Friday before Thanksgiving break, so you've got a lot of time to do that. One thing I will say about submittal 2 is the math portion of it, the computations, are going to be greatly supplemented and assisted by software. You're going to be able to use Mastan to do a lot of the trust analysis for you. So if you have this super complicated trust, don't think you have to analyze it by hand. You don't. So you can use that to check your work, but you don't have to. So, all right, homework 5.7 was due today, and then I'm going to assign homework 6.1 today, due Wednesday. We are entering the land of calculus today. I know. But a lot of the calculus and integration that you need to do can be done with very basic calculators. This, I mean, you can do it by hand if you want, but you don't really need to. It can make your life a little easier. But what we're going to do today is we're going to review the method of virtual work, and we're going to start to get into problems computing deflections. And the way that I have this separated is I have problems involving single moment functions and then problems involving multiple moment functions. And really the calculus is the easy part with this topic. I think the algebra is the hard part and really the introduction of the letter X. So if you can get past that, the rest of it's actually pretty easy. So, so let's get into it. Okay, so hopefully you all had a chance to watch the video that I posted that went through the method of virtual work. Ultimately, what we're doing is we're essentially kind of using the same philosophy for trusses. So for trusses, we were summing, good Lord. So for trusses, let's use this. No, that ain't gonna work. All right, so for trusses, we were summing little f, big F, L over EA for all the truss members. So now what we're sort of doing is summing little m, big M, L over EI, but we're not summing little m, big M, L, we're actually having to integrate. So we sum up the integrals of little m, big M over EI. So it's really kind of the same philosophy. It's just we have to integrate instead of just summing constants because our moment diagrams are variable. They change along the beam, so we have to account for that. Now, I just want to make sure that we're clear on how this works. So what we have to develop, yes? Thank you, Dave. So what we have to do is we have to derive a set of functions, either a function or a set of functions that either represent the real loads or the virtual loads. Now, so basically what these are functions representing the moment diagram. For virtual loads, our moment function comes from taking all the loads off the beam and placing a single concentrated effect on the beam at the point of interest with a magnitude of 1 in whatever assumed direction that we are interested in computing the deflection. If we're interested in deformations and deflections, we place a single unit force. If we're interested in slopes or rotations, we place a single unit moment. Okay? So with before, when we had a set of real forces and virtual forces, now we're going to have a set of real functions and virtual functions that we then ultimately integrate. Now we do still have an E value and an I value, or an E value and then a section property. So like before, we had a material parameter and a section property. Now we have a material parameter and a section property. Only because we're looking at bending, we're not looking at the area, we're looking at the moment of inertia. Now, if you look at this from a units perspective, it doesn't align. We have foot kips, but then we have KSI and inches to the forward. So we have to use some conversion factors. And so I derived these in the lecture video that I pre-recorded. So for deflections, the conversion factor is 1728, and for rotations, it's 144. But since I kind of like my rotations in degrees instead of radians, I take the 144 and I add or multiply a 180 over pi to get the resulting value in degrees and not radians. Okay, let's see. Now, we're not going to have this problem now, but we are going to start to deal with this Wednesday, and that is that if we have multiple functions, or if we need multiple functions to fully define the moments on the beam, we're going to have multiple integrals that we're going to need to evaluate. Now, this is kind of a skill that I'm really interested in harvesting over the next few lectures, so I kind of want to talk about that. So I want to talk about the need for multiple moment functions, okay? So in short, whenever you need multiple functions, this is what's called, the reason that happens is whenever you have a load interruption on the beam. In other words, like if you have a reaction on the beam, if you have a distributed load that commences or terminates, if you have a concentrated force effect that shows up, this is when you need multiple moment functions, okay? Now, an easy way of figuring this out is to quote-unquote move your section cut along the beam, okay? So what I mean by that is once you pass through a new type of load or a load interruption, you need a new moment function. So like, for example, if I look at this beam right here, I have a beam that has, a beam that has a reaction here and a reaction here, and then we have a triangular load, distributed load, triangular load. And so if I ask you how many moment diagram, or how many moment functions would you need to fully define the moment diagram? An easy way of doing that is to take a sort of a vertical line and start moving it this way, okay? So if I look over here, okay, so what about right here? If I cut a section and look this way, what do I see? I see a triangular load, right? But if I move it right here, I still see a triangular load, right? So from here all the way to like right here, it's still a triangular load. But once I pass that point, now it's different, right? Now I've got a triangular load, and now I've got this reaction and this distributed load, right? So I keep going. Even over here, distributed load, reaction, triangular load. Over here, distributed reaction, distributed load, reaction, triangular load. It's not until I get to right here that it again starts changing, right? So now I've got the distributed load, but now I've got two reactions, and now it comes over, right? So this beam would need three mathematical functions to fully define the moment diagram, right? Do you remember that problem that we did in Excel, where you had to plot the shear and moment diagram in Excel? That beam only needed one moment function, right? Because you could, if you conducted this exercise and moved that section cut and looked to, let's say, the left, you would still see the same picture. You would have seen a reaction and a distributed load, no matter which way you put the wherever you put the section cut, okay? This skill is really kind of important for planning out your integration with the method of virtual work. It's not going to matter today, but it is going to matter Wednesday and Friday, because that's going to be basically the main challenge. All right, with me so far? Okay. Now, I want to recall some, before we get into this, I want to recall what happens to the shear and moment diagrams for concentrated force effects. So, why is this important? Because of virtual structures. Virtual structures, you remove from the structure the entirety of the loads, and you replace that with either a concentrated force or a concentrated moment, okay? At the point that you're interested in finding deflections in the assumed direction, okay? So what does that look like? Well, let's take a look at the concentrated force effect, right? So what happens? So you have these stair-stepped shear diagrams, and then the moment diagrams, you have these piecewise linear functions, right? That's what it looks like for concentrated forces. What about concentrated moments? It doesn't change the shear diagram, but the moment you get this sort of like jump, right? That's what happened with moment diagrams, right? So I guess my question would be, let's take a look at these moment diagrams. Do you see any patterns? Every section of the moment diagram is a line, right? They're linear, right? What I am proposing is that for virtual structures, the moment diagrams will always be linear. They'll always be either, piecewise linear functions or stair steps. Every time. There will always be linear functions, okay? So as a result, we can break out the samurai sword or the lightsaber to derive moment functions, or we can go back to basic geometry. Remember the equation of a line, right? We can get the slope of the line, change in y over change in x, but do we even need to do that? I mean, wait, wasn't the slope of the moment diagram just the shear, right? Can't we just do that? Isn't the slope of the moment diagram equal to the shear diagram? And then y minus y1 equals m times x minus x1. We can use that to find the equation for virtual structures a whole lot easier than cutting sections. But we can cut sections if we want. I just want you to know that there's another tool available to you to find m of x functions, or little m functions, I guess I should say. So if we graphically construct the virtual shear and the virtual moment diagrams, we can sort of look at them and quickly derive all of our little m functions. Makes our life a lot easier. Now this observation also holds true for the real structure, but I don't apply that, I don't use that as sort of a general statement, because the real structure might have parabolic moment diagrams and all sorts of stuff going on. So it might be a little more challenging, I guess I would say. All right, any questions? This is going to be the star of the show for today. Let me open up the notebook. Give you all a second. Jot this down. So we have a beam that is subjected, this is a cantilever beam, it's subjected to a uniformly distributed load of 2.5 kips per foot, and we're going to determine the vertical displacement and the rotation at point A on the beam shown below using the method of virtual work. Now, just to make sure that it's crystal clear, I'm going to use these terms interchangeably, the term slope and rotation, and I'm going to use the term deflection and displacement interchangeably. One of the things that, as you're drawing this out, that I have sort of conveniently located for you on this beam is a coordinate system. Later on, and in the real world, nobody's going to do that for you. You're going to have to do that yourself. And I have a lecture, which I pretty much ought to call Dr. Mike's Tips and Tricks, which is literally suggestions and advice for you to do this on your own. Are there ways to define these coordinate systems, and are there ways to simplify this in such a fashion that will make your life a little easier? And I have some strategies, I should say, that will result in less workload. To be clear, you can do it however you want, and as long as you're following the principles of algebra and statics, you're going to get the right answer. But there are ways to make your life easier. So, I'll give you all a sec to jot this down, and then we will get into the land of a beam of deflection. Did you turn to Kokosi? Did you turn to Kokosi?
Still am. Yeah. 2 years, 1 or 2 years.
I got a couple friends that work there, as well as some former students. It's a good company.
Absolutely.
Okay, everybody good? All right. So, in order to assess this, so let's make sure we have sort of our understanding of what we're ultimately doing. Ultimately, what we're doing, whether it's deflection or rotation, is we are summing up the integrals of little m big M over EI dx. This is our goal, okay? And let's not forget our conversion factor. for deflection and rotation respectively? Because we are going to use these. Okay. All right. So in order to do this problem, we're going to need real moment functions and we're going to need virtual moment functions. Okay? So I'm going to start off with the real moment function. In other words, what's really going on the beam. And notice one of the things I'm not going to do is compute reactions. Okay? I'm not going to need them. And when we get into the tips and tricks lecture, you'll sort of understand some strategies that you can employ to negate the need for computing them all together. All right. But in order to handle this, I'm going to need to cut a section. Now let's just make sure everybody was paying attention. How many moment functions am I going to need to fully define this moment diagram? Remember the strategy that you can use by cutting a section and looking, how many am I going to need? Just one, right? Again, the whole theme of today is problems involving single moment functions. So I'm going to cut a section. Right? And then we're going to cut a section, we're going to look to the left. Okay? And I think that's probably pretty advantageous. If I cut a section and look to the right, I got the reaction to deal with, and I don't need to deal with that if I look to the left. So we'll call this real moment function. We'll call that M of X. Section 1, looking left. Pop quiz. If I draw the shear in the positive direction, is that down or up? Down. Cutting a section looking left. Downward shears are positive. Moments this way are positive. That is really important now. Okay? Really important. Okay? Making sure that you're drawing according to positive sign convention. If it kind of didn't matter, now it really matters. Okay? Now, this dimension here is X. Let me move this down a little bit. All right, this is 2.5 kips per foot. So I'm going to collapse that into a single load. How much is that load? 2.5x. And this distance here is what? There you go. Exactly right. So now, if I sum moments at the cut, all right, so if I sum moments at the cut, I have 2.5 times x times a moment arm of x over 2. And then I have m also that way. I don't have any moments going the other way. So I have 0 equals m plus, and so what is that? What is 2.5x times x over 2? 1.25 x squared. So therefore, m is negative 1.25 x squared. Now, I'm going to do something that I haven't yet had to worry about, but I'm going to start introducing this notation now. I'm going to say 1.25 x squared, and I'm going to say 0 15. Okay? And what that means is that this moment function is valid from x equals 0 to x equals 15. Okay? For this problem, doesn't really matter for spec'ing that out. Simply because we know there's only going to be one moment function for the entire beam. But that's not the case for some later problems. And so for some later problems, it's actually kind of important to make sure that you have the moment function and where it's valuable. Okay? So just make sure you have that. Yes?
Would it not be easier just to do find the equation for your shear and then just integrate that?
You can do that, but remember, when you integrate, there's a constant of integration. So then you have to solve for that. And then that constant of integration, for this problem, that value is 0.
Right.
But not necessarily for some other problems. Does that work? Yeah, it works, but in the end, I'm not sure that it's more or less work. That's all I'm saying.
But there's not like a specific reason that you wouldn't do that other than subjective that it's easier. Like, I'm not going to run into problems if I would do it that way.
Exactly. That's right.
Okay.
Because the other thing I'll say is part of the lecture that I'm going to do on Friday is all about what happens when you choose one strategy versus another. And we're going to use problems like this, and I'm actually going to carry that stuff out. And you're going to see, yeah, it works, but you don't want to do it. Because, like, for example, with this problem, if I were to cut a section and look to the left, look to the right, the algebra gets much more involved. You still get this, but the steps you have to take to do that is not worth it. Trust me. So we'll get there.
Okay.
So far, so good? Okay, now let's look at our virtual structure. Now, specifically, the virtual structure for the deflection at A. And why am I saying the virtual structure for the deflection? Because there's two deflections that we're going to have to compute in this problem. This problem is asking for the vertical displacement at A and the rotation at A. Okay? So we're going to need to do two separate deflection problems. So that means we're going to have two little m's. Okay? It's the same real moments on the structure. Like the big M function, I don't care what we're looking at. Big M is negative 1.25x squared. But the little m functions are going to change depending upon what deflection we're looking for. Okay? Now, we're looking for deflection at A. So that means we kick off all the loads that are originally onto the structure and we place a single unit load at A. Now my question is, do you think we should place that load upwards or downwards?
Yeah.
Up? Well, let me ask you this. Take a look at this structure. Do you think point A is going to deflect upwards or downwards?
I guess it's going to deflect downwards.
It's going to deflect downwards. So if we put an upward load, we can work, but we'll get a negative answer for our deflection. I think that point A is going to bend downwards. And if I take this beam and put all that load on it, it's going to deform downwards. So I'm going to take that point load and place it down. Does that make sense? You can place it up. You'll get the same moment.
I was thinking just to balance out. Maybe to leave your
No. You
shear positive, but that
No. You place I understand what you're saying, but you place the load in your assumption of which way you think it's going to go.
Right.
Same with trusses. So my virtual structure is going to look like this. Okay. So that's our virtual structure. We kick all the loads off and we put a single unit load at the point of interest in the direction of the assumed displacement. And so what am I going to do? I'm going to cut it out. How many moment functions are needed to fully define that moment diagram? It's just one, right? So I'm going to cut another section. Some distance x away. And now, let's go through it. Here's the section cut. Again, same direction for shear, same direction for moment. I'm going to call this a little shear and a little moment. Now I'm going to tell you, we are not going to be interested in deriving little v functions for our deflections, but I am going to make a note on what happens if you consider shear deformations. I am not equipped right now to make that because we haven't talked about frames yet. We kind of need to talk about frames first to put that in context. So we'll get there, but not now. There's that. This dimension here is x. So we sum moments at the cut. And so at the cut, we have 1 times x. And then we have m also rotating that way. So again, this is why it's very important to memorize that sign convention. You want to make sure that you're drawing those consistently. Okay? So 0 equals m plus x. So now m is minus x. Notice that that is the equation of a line. Y equals mx plus b. And again, that's also from 0 to 15. That is the hard part. Everything else, this is the easy part. It's not hard, it's just rote. Okay? So let me show you how this works. So the method of virtual work for deflection at A. All right? So we have our little m, which is minus x, and our big M, which is minus 1.25 x squared. E and I were given at the beginning of the problem, 20,000 and 1,500, I believe they were. Okay? So, here's what we're going to do. First thing we're going to do, we're going to handle our algebra first. Let's do little m times big M. So that's going to be, negative, sorry. So that's going to be negative x times negative 1.25 x squared, which is positive 1.25 x to the third. And so therefore, our deflection at A is going to be the integral of little m, big M, over EI dx, which is going to be as follows. So we're going to integrate from x equals 0 to x equals 15 of what? Okay? So let's see. Let's start off with the bottom. We got 20,000. We've got 1,500. Little m, big M, we've already done that, is 1.25 x to the third dx. But hold on. I'm missing something here. What am I missing?
The conversion.
A conversion factor. And what was the conversion factor for deflections?
1728.
1728. So I need to make sure that I'm not forgetting the 1728. Okay? Now everything I learned in Math 229 said that if you have an integral of a constant times a function, that you can factor the constant out, right? So I'm going to make my life a little easier, and I'm going to say that this equals that fraction times the integral from 0 to 15 of x to the third dx. Now, does anybody know, well, first off, that integral, we can do that integral off to the side, but you know your Casio can do that, right? You can just plug that into your Casio, right? Because you could say, now first of all, I'll go ahead and tell you, the answer ends up being 12,656.25, but note, so the integral of 0 to 15 of x to the third dx is x to the fourth over 4 from 0 to 15. And so how do you do that? Remember, you plug in the top number minus plug in the bottom number. What happens if you plug in the bottom number? What are you going to get?
Nothing.
0. One of my tips and tricks is to try and exploit integrals with a lower bound of 0, because it makes the math a little bit easier. And so we'll get into that later on how to do that. So this is 15 to the fourth over 4, which is 12,656.25. But again, your calculator will do that. And in fact, your calculator will do all the integrals that basically we're going to be dealing with. I mean, we're dealing with some pretty simple stuff. Scooch that up. So therefore, what do we get? And we're going to get a positive number, by the way. We'll say 3 decimal places. Make sure everybody's awake this morning.
I got 0.911.
Have a second? So therefore, because it's positive, our assumed direction is correct.
So that's in inches.
Yeah, so keep in mind this right here, so let's put some units on this. That's a good point. Keep in mind, this is in foot kips. This is in KSI. This is in inches to the fourth. They're already in standard USCS units. By incorporating that factor, that converted our final answer to inches. And remember, this is unitless. All right, let me stop for a sec. Anybody have any questions? Okay. What?
Just so if there were two integral equations, like that example problem you had in the slides with the triangular load turning into a distributed load, I'm sure we'll get to, but you would just add those integrals together. So
What problem?
Some of the integrals that you had earlier in the lecture with the triangular load turned into.
Oh, yes. So, okay, and we're gonna get to that, on lecture Wednesday. What'll happen is, so let's say the beam was 30 foot long, you might have an integral from 0 to 10, and then another integral from 10 to 20, and then another integral from 20
But
to
they're all
30.
added together.
Yes, because what you're doing is summing up the energy that the beam is absorbing. So you're summing it up and setting that equal to the external virtual work that you're doing. So that's what, yeah, you're right. That's 100% correct. Sound good? Okay, now, if we want to determine rotation, we need another virtual structure. So in order to handle virtual structure for rotation today, what we do is we say, okay, here's the beam, and we place a single moment on the beam of 1.0. Now, let me show you something. So first off, this is 15 feet. Now, again, pick whatever direction that you want. It doesn't matter. If you assume a direction and you get a positive answer, it means your assumption is correct. If you get a negative answer, it just means you just flip your direction. But I'm going to place this moment going that way, okay? And the reason being is, so, like here's the beam, right? And the original loads were like this, right? This is what the beam looked like. I think that the deformation of the beam is probably going to look something like that, okay? So that means that the slope here is like this, and the slope originally was like that. So if here's what the slope was originally, here's what it becomes. It's got to rotate like that. Hence why I'm placing the moment like this, okay? That's why I'm placing the moment in that direction. To be clear, I could place the moment this way, wouldn't matter. I'd just get a negative answer at the end. So like before, section 1:1, some distance x, v, m, there's my unit moment. This is x, and I just realized something. I have a typo here. This unitless, I said that m of x is unitless. That's actually not correct. This is in feet, and I'll talk about that here in a bit. So now what we're gonna do is we're gonna sum moments at the cut. Okay, so we have 1. Do we do 1 times x?
No.
It's a concentrated moment. You just add the moment. And then m. So 0 equals m plus 1. Therefore, m is minus 1 from 0 to 15. So far, so good? So now we just do the same thing. So method of virtual work.
Does that negative answer mean we assume the wrong direction?
No.
It means we assume the wrong direction for the moment of the cut.
Nope. Bear with me.
Okay.
So m is negative 1. What is big M?
1.25.
No. Big M was negative 1.25 x squared.
Oh, so that's about it.
So when, there you go, right? So little m, big M is going to be negative 1, negative 1.25 x squared, which is going to be positive 1.25. Here's the analogy. When you do a truss analysis, if your real member is in compression and your virtual member is in compression, they're both negative. But then when you multiply them, you get positive. They're both experiencing negative bending. That means your assumption is correct. And so E is 29,000, or not 29,000. I'm such a steel designer, you can tell it's my default. Okay? So therefore, our rotation at A, so now we're using rotation, I use the Greek letter theta for angles, is now we have a similar mm over EI dx. Somewhat similar setup, just some different guts that goes into it. So the integral of x equals 0 to x equals 15 of 1.25 x squared over 20,000 1500 dx, but now I have a conversion factor that I need to use. And what's the conversion factor? It's not 1728, it's 144 times 180 over pi, right? So, like before, I'm going to factor all my constants out. So, don't forget your pi. And then we have the integral from 0 to 15 of x squared dx. This integral, what is that? Anybody have that for me?
I got 1125.
1125. Do I have a second on that? 15 cubed over 3?
Yes.
Yeah.
All right. So that is That's gonna be plus, we'll say 3 decimal places.
0.387.
Do I have a second on that? Yeah. Okay, so therefore, the rotation at A is 0.387 degrees, and it is in the direction of our assumed moment. And I'll talk about this units issue here in a second. So keep in mind, this is still inches to the fourth, this is still KSI, this is still foot kips, but this one is unitless. I had a typo earlier, I said that was unitless. Actually up here, it's in feet. See, that's why the previous calculation had 1728, where this one has 144, because there's an additional foot in there. And just to help drive the point, right? So if I have a section that I've cut, and let's do the same section cut. Let's put a unit moment here, and let's put, or sorry, unit force here, and a unit moment here. And let's put a number. Let's say this is 63 feet. Let's say I cut the section here at 63 feet. Cut the section here at 63 feet. Right? That's V, that's M, that's V, that's M. What's the M here versus the M here? Okay? Well, over here, the M is just going to be 1, right? Because you don't multiply by a distance. So it's just going to be 1, and it's going to be unitless. But over here, what's the moment?
63.
63 what? Force times the distance. The force doesn't have any units, but the distance sure does. 63 feet. So that's why up here, I had unitless there, but then feet there. So I just wanted to make sure I explained that. Because I did that and that was an error. I'm like, whoa, that's wrong. So I need to correct my error. That doesn't go on the mistake counter because I caught it.
We forgive you.
Thank you. I feel, dedicated. So, any questions?
That angle is with respect to the horizontal, I'm assuming, right?
Yes, so like this.
Like that.
All right, I need to show you something with your homework, okay? But yes, you are right. So here's the beam and it deflects, that's how much that goes down. Now, if you wanted to get real fancy, instead of placing your force at the end or your moment at the end, you can place your force or moment somewhere in the middle and find the deflection or the rotation at any point. We'll talk about some ways to do that later. But I do want to show you something with your homework. So this is your homework. What I've done is I've made the problem, instead of like just computing a deflection, I'm actually having you solve for what the I value needs to be such that the beam doesn't deflect too much. So this is actually a little bit more applicable in design land. Now the maximum deflection that the beam can experience is L over 360. These are very common ways of speccing out deflection limits. The only thing I'll say is L over 360, L is the length of the beam. If you take 20 and you divide it by 360, that will give you a number that's in feet, right? So you need to take 20 times 12 divided by 360 to get a limit in inches. So you're going to compute the deflection, but I is going to remain an unknown constant in your integral. Like instead of having I as a value, you're just going to treat I as a constant, you factor it out, and ultimately solve for I. Does that make sense? The integration though is actually easier on this problem than it was on the last one, because you're one order of magnitude on the polynomial down, not up, so. Like if I wanted to make it harder, I'd make a triangular. This is easier. Sound good? We'll pull the code up again, but that's all I got. I will see you all on Wednesday.